Got a lot of material to get through today, and not a lot of time to get through it in. So we're gonna roll. I'm feeling high energy. I'm finally over the cold, so, or at least mostly. So today's lab is on Bash scripting. So the stuff we covered Monday is going to be the stuff that's in lab today. Today we're going to cover functions and arrays in C. Let me just, is that good enough?
Yeah.
Are we recording?
Mm-hmm.
Okay, cool. So this afternoon I am flying out to Romania. So I will be probably not as active on email for the next week or so. I leave you in the hands of the TAs who are excellent. I will still be, you guys will still be able to get in contact with me if you need, if it's an emergency or if you really need to or whatever. Just keep in mind there's like a 8-hour time difference between where I am and where you are, so just keep that in mind. So yeah. Yeah, should be an interesting conference. But anyway, so we're going to talk about C. Oh, by the way, I have pre-recorded the lecture topics for next week. They are scheduled to release today at 12 noon and 1 p.m. Let me know if there are any problems, okay? And it'll probably take me a little bit to get this lecture posted just because I'm going to be on a plane for the next 24 hours and through airports, etc. And then I'll be at a conference, so we'll see how it goes. But anyway, we're going to talk about the grammar of functions, header files, libraries, and the existential plight of humanity, how functions really work, storage classes, scoping, and a few other things, arrays, like tuples but more annoying, and strings are character arrays. So, functions are the basic unit of abstraction in C. You get functions, you get structures, and that's it. That's all of the abstraction mechanisms that C provides, aside from the ability to collect code into other files and use those files using include statements. Functions are highly similar to how Python implements functions. That is to say, pretty much every C-based function will implement these functions in a very similar manner. You should be in a reasonably familiar environment from your Python programming skills. There are a few important differences, however. The return type of the function must be indicated where Python uses the def keyword. So instead of using def, you indicate a data type. Sure. In the absence of a return type declaration, GCC will give a warning and the return type will default to integer. So it's actually possible to omit. Basically, in function declarations, if a data type is expected and not provided, everything will default to integer and not give you an error. So again, you have to watch your code. Curly braces are used instead of colon and indentation. This should be something you're familiar with by now. Arguments must also have data types declared. Again, default is integer. While a return statement is not required, GCC will complain if one is not present. Essentially, functions which do not include a return statement should either be void functions, that is to say, functions which return a void type, that is, functions which do not return anything, Or if it's returning an integer and it does not have a return statement, it'll default to 0. Just like it does with main. So, for example, if we have this function in Python which calculates the maximum or returns the maximum of 2 provided numbers, the equivalent C syntax is as follows. You can see that C is essentially Python expressed somewhat differently. This should be like immediately interpretable to you. Note curly braces instead of colons and indentation. Note presence of semicolons. Note if statements work basically exactly the same, right? Note the inclusion of data types. Any questions so far? Should be pretty straightforward, right? Don't worry, it'll get harder. Let's take a look at the following poorly written function. Right? Notice no return these return statements have been commented out. And everything has been squooshed together on a few lines. Still valid C code. Also, notice the absence of declared data types for the return type and arguments. While this will technically compile, the following warnings are found. So, warning, return type defaults to integer for max, in function max. Warning, type X defaults to int, type Y defaults to int, control reaches end of non-void function. So basically this function will do nothing. It'll return a 0. It thinks everything is an integer, which actually is true, but GCC will give you warnings about it. So the thing about GCC and other programming in most languages, you definitely want to pay attention to the warnings. Although a warning will not prevent compilation, it is perfectly possible to program C code without triggering any warnings, and basically the purpose of these warnings is to say to you, I am applying some kind of implicit rule that is in my language semantics. However, this may not be what you intend, right? If it is what you intend, you can codify it in the code itself so that you don't get this warning anymore, and the code will be explicitly what you intend it to be, right? So warnings are important. Pay attention to warnings. It's easy to write a C program with several hundred warnings if you're working on a big project. So, function prototypes. In C, as in Python, in order for a function to be in scope, it must be defined before its use. So in Python, you have to put the function declaration before its use. The same thing applies in C. If the function max were defined after its use in main, GCC produces this warning. Implicit declaration of function max. Did you mean main? So C will do a very slight degree of spell checking on function names. That's what it's doing here. It thinks that you misspelled main as max, so that's why it gives that warning. But it turns out in C that because of tricky things that you can do with a compiler, you can with the compiler, you can actually include functions which are defined nowhere in either the main file or any of the included libraries, so long as you include that at the compilation phase. So this is a warning because max might be brought in during compilation and might not be included anywhere in the include hierarchy. It could still be a valid program. Basically what that means is that a definition for max might be found during the linking stage rather than the compilation stage, right? So that's why this is a warning and not an error, right? But the other thing to realize is that this warning if not resolved by the time you get to linking, will become an error. So that is to say, this is a warning that becomes an error if a definition for max cannot be found during linking and prior to execution. Any questions about that? Cool. So, early versions of C did not check for correct function usage at compile time, so the error would show up at runtime. Fortunately, we live in a more advanced age. Function prototypes solve this problem by having function typing information available while maintaining C's back compatibility. That is why this is a warning and not an error. So the idea of a function prototype is actually borrowed from C++. So there has been a certain amount of cross-pollination between C and C++ over the years. Function prototypes were sufficiently useful, they decided to include it in C. So, a function prototype is the following line of code. Ordinarily, you include this at the top of the file, right underneath the include statements, right? Notice, it's exactly the function declaration line, but terminated with a semicolon instead of opening the definition with a curly brace. What this does is it tells the compiler what the typing information for the function is. It's like a promise, I'm going to define this somewhere in the file, right? If you have included a function prototype, the actual definition for the function may be included anywhere within the file the function prototype is in, or even inside of some included library file. As we're going to see, you can actually split up function prototypes from their definitions and put them in different files. In that way, you sort of have one file which describes the function interfaces, the API, for some library, and then the actual implementation thereof exists elsewhere. So, a function prototype is syntactically the first line of a function declaration terminated by semicolon. Pardon me. It is good practice to put function prototypes immediately after your preprocessor commands, i.e. your include statements and any define statements you might have. If it's right at the top, basically the same rule applies to function prototypes that apply to function declarations with respect to the order in which things happen in the file. It doesn't do any good to include a function prototype after the function's use in another function. You need to include the prototype before its use in another function. Question?
So the function prototype is similar to the interface of the Java. It's just it does no things, but maybe we can develop more things in the future based on this. So we just leave it here for no thing.
I'm not sufficiently familiar with Java to know what a Java interface is, but it sounds like it's the correct idea.
So for example, we don't know what we can do for this function, but maybe we will use it in the future. So just leave an empty function here.
Precisely. That's a great way to describe it. It's an empty function. It tells the compiler what information it needs in order to compile it. It knows what the input types are, the output type is. That's enough to be able to do type checking to the degree that C type checks. But the actual definition can be provided later. Question?
Does the syntax for the definition change if you have the prototype?
No. Nope. If you're using a function prototype, you just include the full function definition later on the same way you would normally. Good. So, this line declares the function up front so that its definition may now occur anywhere in the file without generating any warnings. So how it works in C normally is that the main function is usually the last function in your file, because it will require all of the other functions in the file, right? Now, perhaps you think that that's a little bit stupid, and perhaps you'd like to put your main function at the top of your file because it makes sense to put, the top level details at the top of the file. Maybe that's the way that you want to do things. If you use function prototypes, you know it no longer matters what order you put your functions in, so you can rearrange them however you like, in a way that makes sense to you. Good. So, let's talk about library architecture. Computer architecture is a set of rules and methods that describe the functionality, organization, and implementation of computer systems. To understand library architecture is to understand a great deal about how it is computer systems work, sort of even at the kernel level. So, header files versus libraries. Things that are useful. The ability to call functions defined outside of a source code file. The ability to pre-compile these functions. The ability to share library functions among many programs. These purposes are served by the library system. Libraries are composed of two pieces primarily. You have header files, which contain the prototypes of functions made available by a specific library, and you have the library file itself, the files in which functions are specified in the header file. The functions from the header file are implemented in the library file. There are two primary types of library file, static and dynamic. See next slide. Because their functionality is so closely linked, when a person says a library, they usually mean both the actual library file and the header file taken in combination, right? So if you import a library, like for example, include stdio.h. You're not just including the header file is also bringing out the actual implementation of the standard I/O functions, right? But when you sort of think about it, you think about both of those things as being one thing. Make sense? Any questions? Good. So, static versus dynamic libraries, right? So the word static is derived from the Greek statikos, meaning causing to stand. Dynamic, derived from the Greek dynamikos, meaning powerful. So, in static libraries, object code is linked with a program and then is integrated into an executable at compile time. That is to say, up front. Consequently, the compiler needs to be able to find it. So, static libraries are compiled into the executable during the invocation of GCC, right? You need to have all of the code up front, and you compile all of it at once. Now, there are advantages to this approach, but in order to discuss the advantages, let's talk about dynamic libraries. So, dynamic libraries are linked to the executable at compile time, but the implementation of the linked function is loaded at runtime. So, with a dynamic library, you do have to tell the compiler where the dynamic library is, because it needs to create a symbolic link to it. However, that link is not followed and the code is not retrieved until the program is actually executed. Linking resolves undefined references in the source file, and these dynamic libraries may be shared among many programs. Any questions at the moment? Okay, so what does this enable? It enables you to have library files stored somewhere in the operating system, which the operating system may update, right? And those updates will be seen in any program which dynamically links to them. This is part of the entire purpose of dynamically linking libraries. So, you know, so you're running your little, program that does, FTP transfer or something like that, and it uses C libraries. And one of the C libraries is updated to provide better security, some fix to some exploit that someone found, something like that, right? Under dynamic libraries, if that's a dynamic library, your file transfer protocol program automatically acquires the update because it doesn't use that code until it's running, right? Incidentally, this code will be in a pre-compiled binary, so that it doesn't have to compile it when it runs it, it just runs it, right? In a static situation, the compiler will take the actual code that is contained in the library, integrate it into the executable at compile time. So, in order for a statically compiled program to acquire the update, the whole program would need to be recompiled. Normally, for end-user programs, they are only compiled at installation or reinstallation. So, dynamic libraries allow updates where static libraries do not. Does that make sense? To some degree?
Repeat the last one.
Yeah, so because dynamic libraries link to a library that's sitting in the operating system, if the operating system updates that library, it's automatically seen and executed by the dynamic library. Whereas static compilation requires you to take all of the code that this program needs, crunch it all up into the compiler, dump it all into one executable at one time. So, it can't get updates, right? It would need recompilation to be able to get any new code that the operating system might update the libraries with. Does that make sense? So one might ask oneself, well, why would you ever do static compilation then? Answer, sometimes updates break things. Sometimes, because it's a dynamic library, now people try to be pretty careful about this, but it happens. Sometimes an update to a library will break things dependent on that library. A dynamically linked library, or dynamically linked program will break at that point, whereas a static one will not, because it isn't using the update, right? Cool. So, there are two ways to include files. The first is the one we've seen so far, with the angled braces. The second is to use quotes. If the file name is enclosed in quotation marks, GCC will search both the first relative directory of the current file and a pre-configured list of standard system directories. So, if you are including a file which you wrote, you need to use quotes. If angle braces are used, only the standard system directories are searched. So angle braces will not look in your current directory for files that you may have written. Technically, this means you could use quotes for everything, but by convention, if it's a standard library header, use angle braces. It's kind of like a, read-only thing, type thing, It's a way of distinguishing the standard library. It will also tell you if you misspell the standard library name, whereas this, it'll give you a different type of error that's less useful. Any questions about that? All right. So, from the GCC documentation, which is something everybody should know where to find. If you just Google GCC documentation, you'll find it. Header files serve two purposes. Number one, system header files declare the interfaces to parts of the operating system. You include them in your program to supply the definitions and declarations you need to invoke system calls and libraries. Your own header files contain declarations for interfaces between the source files of your program. Each time you have a group of related declarations and macro definitions, all or most of which are needed in several different source files, it is a good idea to create a header file for them. So, system header files are things like stdio.h. Your own header files are ones that you may write for your own project. As we move through the labs, you'll see there are a few different instances. I believe Lab 5, actually, you'll be required to create your own archive and libraries, which is fun. So I'm going to add, in the lab, you'll be actually expected to produce these. Fortunately, all of the information you need is in the lab, and if it isn't, GCC documentation exists. So, by convention, header files have the .h file extension. Although, again, at this lower level, file extensions are a somewhat ephemeral construct. So, here is a rough list of some of your standard library, the standard libraries. Assert.h contains information for adding diagnostics that aid program debugging. So assert statements in C basically work the same way they do in Python. They will although rather than causing an exception, because C doesn't have exceptions, it will just immediately terminate the program with an error. So there's no way, well, I shouldn't say that. There are ways of handling that sort of thing, but it's not an exception handling system. There's no such thing as a try except block in C. ctype.h, character tests, testing for is a character capitalized, that sort of thing. Error number defines macros that are useful for reporting error conditions. Float contains floating point size limits of the system. Limits contains integral size limits of the system. Things like how big is an integer are defined in limits.h. Locale contains function prototypes and other information that enable, dates, times, currencies, that sort of thing. Locale. You don't have to worry about these two, really. Math.h is really, really important, though. That contains your definitions for things like sine, cosine, square root, all of your math functions. As exact definition of pi as you can get in floating point arithmetic, that sort of thing. Set jump contains function prototypes for functions that allow bypassing of usual function call and return sequence, but you don't have to worry about that. Signal.h, this is roughly speaking the way that C does error handling, but we won't have to worry about that just yet. Skip that one. Standard definition contains common type definition used for C performing calculations. Also, a bunch of very useful things, including dynamic memory allocation, which we're going to talk about next week when you watch the videos. Standard I/O, self-explanatory. Standard lib. Oh wait, I'm sorry, this one's the memory allocation. Yeah, standard lib is memory allocation. Standard definition is just type definitions. String.h contains functions for string processing, time.h, manipulating time and date objects, except objects don't exist in C. And one that's not included there is standard bool. You can't have booleans if you don't have import the library for them. So, here is an example of a very simple library. Top.c includes mylib.h. Mylib.h includes the function prototype for max. Mylib.c includes the definition for max. I apologize for squishing this up, but I wanted to fit it all on one slide. Any questions so far? We'll see how this is actually linked up. One very important thing to note here. Neither top.c nor mylib.h include mylib.c. So mylib.c, if you just examine which files import which files, mylib.c is not imported by anything. Yet, it contains a definition referred to by mylib.h. We are going to resolve this discrepancy using the compiler. So, note that mylib.c does not contain a main function. That's the other thing to note, is that it only contains a definition for max. It doesn't contain its own main function. All three of these files are compiled and linked with a single invocation of GCC. GCC wall. By the way, have I told you guys what wall does?
Yes.
No.
It enables all warnings. So there are some warnings which GCC considers, less important, which it hides from you by default. wall shows you all warnings, and it's useful to actually get rid of all warnings. At any rate, top.c and mylib.c are included in the GCC invocation. We then use the O flag to specify top as the output executable name. Running GCC on only top.c, omitting mylib.c, will result in an undefined reference, which is an error. However, if you include mylib.c here in the GCC invocation, you're all good. Question?
So, in the slide you showed before, there was no include statement for the mylib.c.
Yeah.
And so you're saying you can include it later on when you call GCC.
Yes.
Thank you.
Yeah. Basically, GCC will take all of the files that you give it and sort of crunch them all together into one executable.
Okay.
Question?
Is there a reason for the header file in that?
Yes. So let's imagine that you're working on a project that has 12 to 20 developers all working on it, right? The header file is a contract. What you do with the code in the header file, under a good group development practice, the contents of the header file will be decided on in a committee, because this forms the interface between the people who are working on top.c and the people who are working on mylib.c, right? It's an agreement between the two of them. It's like, the mylib.c guys say, okay, I will implement it according to this, this, and this, but I'll need this as input to the function. The top.c people agree, I will provide you the inputs as specified, but you need to return me this, right? So, in theory, This guy gets set and modified relatively infrequently during the development of the project. Both of these guys, like in modern terms, you would say front-end developer, back-end developer, right? Agreed upon API. It makes sense to separate that out as its own file, right? Particularly, you know, if you bring this into the like the concept of the Git repository that you guys have been learning so far, merge conflicts here are only conflicts between different back-end developers. Same thing here. Merge conflicts here are only disagreements between front-end developers. Merge conflicts here would be like disagreements between anybody on the project. So it makes sense to put that to the side, lock it down, don't touch it, don't modify the interface, right? Unless it's like critical that it be modified, and in that case there should be like company procedures for informing everybody how things are being modified. Does that make sense? It's like, if you're just looking at it from the perspective of like an individual C programming project, like a hobby project or something like that, there's really no reason to do something like this, right? But that's not what I'm trying to teach you in this class. I'm trying to teach you how it is that you people will become software developers who work with other software developers. And that means learning what's conventional and how to organize code so that it sort of organizes a project, right? Make sense? Not to mention, this is the way that the C standard libraries have been done, and if it's good enough for Linus Torvalds, it's good enough for you. Make sense? Any other questions? Question?
My question is maybe it's dumb, but
That's fine. I love dumb questions.
okay. So MATLAB.h is necessary for the whole system, for the whole thing, for the whole project here. It's like the background of MATLAB.c.
So there are a number of alternative ways you could approach this, right? This definition could be included in this file,
Yeah.
like above main. That would be one way of doing it, but that wouldn't use libraries at all, or that wouldn't use included files. You could include mylib.c and skip the use of the header file,
Can I
right?
try to explain it?
Sure.
And check my explanation is correct. So top.c is a main file, and we want to define a function, max function, and we define in the MATLAB.c. We can do it like this way. I mean, include the MATLAB.c node.h. It still works, but we still need the MATLAB.h. We separate them. Is for better future development, cooperation with others. I mean, it's more clear and more organized. Like this.
Yeah. There's also another reason to do it this way. By not including this code here, it allows this file to be a pre-compiled shared object file. So mylib.c might be C source code that GCC has to chew through. It might also be an object code file which has been pre-compiled. And then, like, pre-compiled libraries can be used as using a similar mechanism. Yes?
So for this, we have to compile both mylib.c and top.c at the same time.
Yes.
Can you include it in the header file?
Can I include what in the header?
Sorry, mylib.c in the header file, so you only have to compile one.
Yes. Yeah. If you just, like, two ways to do that, right? You can either include mylib.c here, like, or even change this h to a c, right? Then it would work, right? You could also include mylib.c inside mylib.h. That's a thing that I think you probably will see in one or two of the lab codes that, codes. I hate it. It's called a program. It's, that's something you'll see in a couple of the lab programs, example programs that you'll download. Yeah, there are like at least 6 ways of doing this, right? However, this is the way that allows mylib.c to be a pre-compiled file, so that, which is kind of the point of the library, is that it's been compiled before you get to this compilation stage. Make sense?
Mhm.
Cool. So, good. I think I'm about to say everything I just said on this slide, but I'll go through it quickly. It is a stylistic recommendation to write header files for your C files below the top level, especially if they are large. This emulates the way other programming languages use packages and modules. However, the header file may be successfully omitted in the previous example. If you change mylib.h to mylib.c in line 3 of top.c, everything works. Omit mylib.c, you may then omit mylib.c from the GCC invocation. GCC has to know where to find the code. If it's not in the source code file itself, it needs to be in the compiler invocation, right? One of those 2 places, but it doesn't need to be in both. Make sense? Cool. So, the procedure for creating a dynamic library is operating system dependent, but the goal is to create either a shared object file, .so, in Mac and Linux, or to create a dynamically linked library file, a .dll file in Windows. How many people have heard of DLL files? Oh, you guys don't root around in the operating systems?
So it's before, but I don't know what's the usage of it.
This is the usage of it. Basically, it's a precompiled library file that your program will load at runtime. So, yeah. If set up properly, a dynamic library can be used by programs written in languages other than C. So, not only are shared libraries a interface between C programs, C++ programs can load them. Julia, which is a new language, can load them. Rust can load them. Java can load them. Python can load them. That's because libraries are a universal interface. So long as the programming language knows how to load a library, basically, if it can load printf, which Python does and renames print, it can load pretty much any code that you write in C. So, be warned, messing around in your operating system's hidden folders can have serious consequences. Never mess around with a computer like this if you don't have your data backed up, and don't say your prof didn't warn you. One of the lab activities in this course will require you to create and install shared object libraries. So that will be lab 5, I believe. And this lesson will pick up there. For us, we need to keep moving. So, speaking about, okay. And now for something completely different. Let's talk about the call stack. So, sort of generally on our discussion of functions and how functions work. So, have you ever wondered how your computer keeps track of all those function calls? Function calls are stored in your system's function call stack, or just call stack, or, reverently, the stack. The call stack has a fixed or static size. If too many items are added to the call stack, this can result in an error called stack overflow, which is where stackoverflow.com, that's what it's referencing. So now you know. In order to understand the call stack, we need to know some rudimentary data structures. So in order to know what a call stack is and does, we first have to know what a stack is and does. So a stack is a data structure that always returns the most recently added element. It is also known as a LIFO buffer, last in, first out. There are two primary operations on stacks, push and pop. So when you add something to the stack, you push it to the stack. When you remove something from the stack, you pop it from the stack. The kitchen metaphor is a stack of plates. So think about the plates in your cupboard in your kitchen, right? When you need a plate, you pull it, the top plate off of the stack of plates, you use it, right? When you wash a plate and put it back in your cupboard, you also put it back on the top. This effectively means that for most people, they only use like the first 3 plates of their collection of plates, right? But that's fine. And if you're like me, you also have like a similar system going on with socks. So you'll have like half of socks, which are in very poor condition, and then like the whole rest of your collection of socks are in very good condition because they're never worn because they're at the bottom of the stack. Anyway, so another, like in a more programmatic example, undo and redo actions in many programs are stored in a type of stack. The stack that most programs will use have the ability to delete the oldest operations if the stack has grown too large. So, maybe your image editing program only keeps a record of the last 32 operations, right? So this is how it would work, right? You have a stack, right? If a new element gets added to the stack, it gets placed on top, right? Say fill red or whatever, some operation, right? These being other operations. If the user requests an undo operation, this command is extracted from the stack, it's run in reverse, right? And effectively removed from the stack, right? So then the next operation that is queued for undoing is the one that occurred previously, right? So, whatever it was, that's the next one. The other, an undo-redo system will also have the ability to take the earliest element that was added and remove it from the stack if the stack exceeds n elements, right? Now, operating systems don't do that because the first processes that are invoked inside your operating system are things like the kernel, right? So you don't want to throw that away, right? But this is essentially, this is the model, right? So, So in essence, this is a visualization of how a stack works, right? You have a stack, you push elements onto the stack, right? And then they are popped off in the reverse of the order that they were added. Any questions about this so far? Being able to program a stack is like a very common interview question. It's right up there with doubly linked or singly linked lists, which we're also going to talk about in this class. So, the call stack then. The call stack enables programs. I'm getting feedback. Is the feedback okay? Because I can just shout at you guys. Is it too annoying? Let me know if it gets too annoying, okay? So the call stack enables programs to step into functions while keeping their place in the program that called that function. Functions are properly thought of as sub-programs. So this supports the creation, maintenance, and destruction of each function's local variables. This is sometimes known as a namespace. It's also sometimes known as a stack frame. So the stack frame will also keep track of the return address that each function needs to control the invoking function. So think of this previous example with the numbers, but replace the numbers with all of the data necessary to execute a function, including variables. These are known as stack frames. So this is how it works. System memory. The region of system memory which is dedicated to the call stack. All right? You will have stack frames. Right? Let's say you run your C program. Right? A new stack frame is added, and like there's a reason I'm like going from like top to bottom instead of bottom to top, because like that's how it actually does it in terms of memory addresses. But you know, you guys don't have to. This is the bottom, top. I know that's like the reverse of how things are in like regular life, but you know. So anyway, so we add a stack frame, right? That's you know, like, you know, let's say, you know, foo.c or something like that, right? This region of memory, which is allocated to foo.c by the operating system, will contain local variables, right? It will include various, like, you know, return address of, like, you know, this guy. It'll contain the information needed to send information back here. What happens with this guy, once a, like, well, let me add another one. So let's say foo.c calls a function, right? It adds a new stack frame, let's say like max, right? Max function. There we go. All of the local variables for max will be stored here. With respect to max's stack frame, these guys are now global variables. Does that make sense? So looking down the stack, you see global variables. At the top level of the stack, you see local variables, right? So that's how scoping actually works. One of the things that gets stored in foo.c's stack frame is the point in the program that it was at when this function call happened. So program pointer equals, you know, some number. The position in the program is stored here. When this guy finishes, a return value is sent up the chain, right? So the return value is returned. This stack frame is deleted, the space freed, and the program pointer is loaded from this stack frame back into the CPU, which continues on, you know, executing it. So that is why local variables are destroyed utterly when the function ends. It's because the memory that is allocated to that function by the operating system is deallocated and returned to the operating system. So the variables literally no longer exist. And if a function calls a function, you know, you get function stack frame plus another function stack frame. If you have a recursive function which calls itself many times, it's like stack frame, stack frame, stack frame, stack frame, stack frame. This is the reason that recursion is not the most efficient solution unless it has algorithmic advantages in languages other than Haskell. Haskell handles it handles functions without using the system call stack, which is how it gains that level of efficiency. Because if every Haskell function had to be put on the call stack, then it wouldn't be an efficient language at all. But anyway, cool. Any questions? This is a little bit of computer architecture for you guys. Incidentally, stuff that is like not all what we would consider local variables are stored in the stack frame. Stuff that you allocate yourself through dynamic memory allocation, which we'll talk about next week when we get to pointers, that's stored in a different type of memory called heap memory. But we're not going to get into it too deeply. You'll get into it more deeply when you take 2GC3, whichever the architecture course is. Anyway, so let's see here. Right, so let's talk about the difference between pass by reference and pass by value, right? So there are two main ways that a programming language will pass data into functions. You have pass by reference, which is used in Perl, Visual Basic, and Fortran. In pass by reference, variables are passed into functions as references to data rather than the data itself. This means that modifying a function argument inside of a function will modify the variable passed into that function within the context of the calling program. Pass by value is used by C, Java, Python, C++, all of the more strongly C-based languages. Python has a little asterisk because it technically uses pass by assignment, but assignment values are values, so it's still technically pass by value. The bit values of the variables are passed into functions rather than references to the memory that they are contained in. Modifying an argument does not affect anything outside of the function's local context. You can think of arguments passed into the stack frame as being local variables, whereas in something like Perl, what you actually get are references to stuff that exists in the calling frame. So, C can pass references using pointers, but you have to do the legwork yourself. So C has the ability to pass references, but it passes those references by value. So a memory reference is a value in C, and those get passed by value using pass by value, but so C essentially can pass by reference if you tell it to, but otherwise it will pass by value. Make sense? Sort of? A little bit? Am I losing you? This will make more sense once we've done pointers. So, there's just a little bit of miscellaneous stuff. Typedefs. Let's talk about defining our own types. So the typedef keyword allows us to define type synonyms. So you might have some, some type that it's long to write out in C, so you want to give it a shorter name. Typedef followed by the type that you want to create a synonym for, and then the thing that you want to give it, the name that you want to give that type will basically tell the C compiler, anytime I find this, replace it with that. But this can improve readability. So characters are stored in 1 byte. However, signed or unsigned, it's a question. So an unsigned character is a byte. So that this line declares it so that you can use the byte keyword anywhere that you would use unsigned char. So this allows us to use the new type byte anywhere a type must be declared. The compiler will swap the type's synonym at compile time. Type synonyms can be very useful for improving the readability of your code, and they allow for more descriptive type information. By convention, data types are capitalized. We are going to see, so to speak, that when we study structures, we're going to see typedefs again, because if you have a structure, you have to, like, for some reason, whenever you use a structure type, you have to include the struct keyword everywhere, which is just like huge and annoying, and so typedefs are used to sort of simplify the syntax somewhat. We'll see it when we get there, don't worry. Another way we can define custom data types in C is using enumerations, and this will probably be a new idea, a new concept for you guys. So, enum starts an enumeration. You choose a data type name, in this case Pokemon status. You then provide a number of enumerats, or things which are enumerated over. Things of this type may be any of these values. So basically it's you specify a type, you specify a bunch of different values that type can hold. It can't hold any types, it can't hold any values other than these, except that under the hood, it's like 0, 1, 2, 3, 4, 5, 6. It's just, again, it's going to replace these for integers ultimately inside the compiler, but for the purposes of writing the program, it allows you to make it more pretty. So, like, for example, Pokemon status, stat equals none. If stat equals poison, then HP is equal to HP minus HP divided by 16. If HP is less than or equal to 0, status is equal to faint. It allows you to, like, do things somewhat more descriptively, somewhat more usefully. Does that make sense? Question?
So can I understand the enumeration? Wait, is my pronunciation correct?
Enumeration.
Okay.
Yeah.
So can I understand enumeration type as? I mean, for example, Pokemon status is a set of data, and the type of Pokemon status can only the data of the type of the Pokemon status can only be one of the set.
Yeah.
Okay, got it.
Question?
Yeah, earlier when you did the typedef thing, do you have to declare, like, so for char, could you just put typedef char, or you have to say unsigned or signed?
No. You can swap this for whatever you want.
So it could be an int or a float or...
Yeah.
Okay.
Or like even array types.
Okay.
Basically, that bit, any valid C type, including other type definitions.
Okay, thank you.
Any other questions?
So, sorry.
Yeah, this one?
No, back.
Yes.
I'm still confused. What's the uses of the char here? I mean, that is a type of data we created, but why we added a char before that?
It works a little bit like this. So, typedef tells you you're defining a type, right? And so you've got, this and that. In this case, unsigned char and byte, which is something we've defined. You should envision a little bit like a little equal sign between them, right? So, like, I'm saying for the purposes of this program, like, int is, my type. Then anywhere my type is found, int will be replaced for it.
So my type is not a new data type.
Yeah. A new data type, but derived from an existing one.
So it will have the same usage as the copying.
Exactly. Yeah, exactly. Like, all integer operations will operate over my type as you would expect them to.
So we can note that for example, my type 4, if it, I
you could say like, my type x is equal to 3, you know,
Can
x.
we say x equals to, for example, a string?
Strings are character arrays, but yeah, you can do that as well. Yeah, if you want, you can say character array is string, but you know. Does that make sense?
Yes.
Cool. All right, moving swiftly on.
So we just add one more name for the like in, which is add.
Yeah,
Oh, okay.
yeah. You know what a synonym is?
Pardon?
A synonym, like when one word means the same thing as another word.
Yes.
That's what that is.
Oh, I thought we created a new data structure.
Not yet. When we get to structs.
Oh, that's why I was confused. Now
Yeah.
I got it.
Okay, cool. All right. So, in reality, each of the enumerats is an alias for a literal bit value. We can expose these with the following program. So, if you print as integer what each of these is, then you'll see it's 0, 1, 2, 3, etc. But what the enumeration allows you to do is pretend they're not integers, right? Just like all programming allows you to pretend that whatever you're working with isn't an integer. You know, like Boolean data types allow you to pretend that Booleans aren't integers. Floating points allow you to pretend that it's not an integer in the underlying representation. But anyway, just like Typedefs, the main purpose of enumerations is code readability. Otherwise, you're basically, whoever's programming it or reading your work will have to manually translate in their head between all of the different, you know, status codes and what they mean using like a table or something in some piece of documentation buried somewhere in the project. So, good. We can change the scope of identifiers in C using storage class modifiers. So these are keywords that can be placed before types to declare, for example, a variable in different ways. So auto is stupid and applied automatically, so you don't ever have to apply it explicitly. Extern makes it external, so basically it makes it global. Extern is the C equivalent of a global variable. Static declares the variable within, so it's still scoped to the function that you declare a static variable in, but a static variable will hold its value through subsequent calls to the same function. So it will preserve its values through the function being, put on the frame, taken off the frame, put on the frame, taken off the frame. It's still local to that function, but it's stored in the data segment rather than in the stack, right? So it's being stored differently, so it won't be destroyed by a function being returned. Does that make sense? That's what a static variable is. Registers are stored in the CPU register. Basically, register memory is the most efficient form of memory in terms of speed, but and C will allow you to suggest to the compiler that a particular variable gets stored in register. This is the sort of thing that, like, if you turn optimizations on, GCC will figure out which of your variables are more efficiently stored in register memory as opposed to regular memory anyway. So it's like, this is at best a suggestion, right? You can say, hey, GCC, I suggest that you store this variable in register memory. And GCC will be like, well, I will consider your suggestion. But that's about as far as it goes. Whereas these are like, much more, you actually take control. C cannot give you access full undiluted access to register memory. Most architectures I've seen only support 16 registers. So you can imagine that you would run through them pretty quickly if you were like, oh, register memory is more efficient, so I'm going to make all of my variables register memory. Yeah. I'm going to make 300 register variables. It's like, yeah, okay. So, let's talk about arrays then. Yeah, I'm running out of time, so I'm going to skip this. Skipping. All right. So, in Python, you have many data structures to choose from. Tuples, lists, dictionaries, sets, and strings. In C, there is only one, the array. If you need something more complicated than an array, you have to either find a library defining it, or define it yourself. C, so it's not like these things can't exist in C, because that's how Python implements them. Because Python, a lot of it under the hood, is actually in C. So, like, you can have dictionaries, but you have to find a library for them or write them yourself. And, you know, generally you're sacrificing a lot of efficiency for them anyway. So, what is an array? An array is a continuous and contiguous set of segment of memory which may be accessed via linear indexing. So basically, it's like somewhere between a list and a tuple. So statically sized, right? So basically, when you declare an array, they get declared with a certain size, right? The system allocates you a set of a block of memory, that precise size, and that does not change through execution. That is a property of arrays. Yes.
I remember that there are some algorithms need to, like double the size of array during the, when the algorithm was running. So this kind of algorithm cannot be implied in C.
It cannot be implemented in C without using dynamic allocation libraries.
Oh.
So you can create arrays which can be resized, but right now we're talking about the sort of native static arrays. We'll talk about, like, in order to understand dynamic arrays, we really need to do pointers, and we're going to do that next week, right? Basically, you can't create an array using the static array syntax and then resize it. You must create the array using the dynamic allocation libraries. Then it can be dynamically changed. That's because it gets stored in different memory, right? Pretty sure this gets stored in the call stack. Properties of arrays, which are different from properties of tuples and lists and all the rest of the Python data structures you know and love. All elements of an array have the same data type, right? Not only are they statically allocated, they are monotyped. So this business in Python where you can have a string here and an integer there, no. Everything is integers, or everything is characters, or everything is pointers. One data type. Arrays use zero indexing for reasons that we're going to explore when we get into pointers. But that should be no surprise. Arrays are static. The size of an array does not change during execution. This means that the size of the array must be known at the time of declaration. There are ways of getting around this, but not without using pointers, which we'll talk about soon. So basically, So, an array is declared in the following manner. Int C square braces size indicated. X here is the size of the array. Note that x must be either an integer literal or an expression which evaluates to an integer, like 5 plus 7. This rule applies to array indexing as well as declaration. On declaration, arrays are filled with smelly garbage, junk data, meaningless sequences of zeros and ones. Arrays may be indexed using the array index operator, which is the same in C as it is in Python. Open square brace, number, close square brace, that accesses a particular element of an array. So unlike tuples in Python, the elements of an array may be assigned to. So this is a valid statement, right? Any questions so far? Yeah, this should be reasonably straightforward, right? So this operation binds at the same level as function calls, so very tightly. So it binds so tightly that most people don't even think of it as being an operator, but it is actually an operator. If you dig into it, we'll see that next week. As we'll see later, the index operator is actually syntactic sugar for some pointer operations, but again, we need to talk about pointers first, so we'll leave that for next week. So, here's an algorithm for pretty printing arrays. Pretty printing just means printing in a way that's pretty. Sometimes the terminology is exactly what it sounds like. So, include stdio.h, sure. We have main, we declare an integer array of 12 elements. We declare a floating point array of 4 elements. You know what? Let's just run this thing. This is not quite what I was expecting. Okay, so here's the program. We'll compile arrays.c. So, this is how you declare a string, right? Foo is actually too large for the declared size. This is an array that's been declared with 2 elements, and this string actually contains 4 elements, despite the fact that it appears to contain 3. The reason for this, as we're going to see later on in this lecture, all string literals are implicitly terminated by the null character. That's how, that's like a very, very old convention that's built into the standard libraries, which lets the string libraries know when it's reached the end of a string so that it can stop processing. Basically, when you're programming with arrays, there are a lot of things which don't exist. There's no length function. So if you pass, there's a size of function, but it only applies when the thing's in scope. If you pass an array into a function, you must also pass the size of that array into the function if it does not contain a terminating character or a terminating value, like a known terminating value. C does not know how large its arrays are. You have to tell it how large its arrays are. So, for example, when I'm printing all of the elements of this array, right, I'm actually hard coding the size. Let's run this thing, see what it does. Yeah. So in the first place, foo itself is a memory address. This is what a memory address looks like. Second of all, notice how I'm declaring it as size 12, right? But I'm not initializing it anywhere. It therefore contains random values. These are the random values. Those are the random pieces of memory that are applied. And you can see that every time I run this program, I'm getting different values. It's garbage data. Although there are patterns to it, those patterns can't be relied upon and do not indicate anything meaningful, right? So here's a little fun thing. This thing is supposed to be of size 12, right? What happens if I put 13 here? What would happen in Python?
Get an indexing error?
You'd get an index error because index 12 is not included, right? Because 11 is the last one. So what happens if we do this? It just doesn't. It has read and printed an element that is outside of the scope of the declared array. It is also containing garbage data, but it's done it. Not only that, did we get so much as a warning? No, that's that warning from here earlier. Welcome to the Wild West. This is C programming. I'll just let that one sink in for a moment. So there's a reason that this happens. Basically, your array is a pointer to memory. The indexing operation is pointer arithmetic. It just moves the pointer over, however many spaces and then reads that value, right? And then does whatever you want with it. But the fact that we were able to do this means that C isn't checking to make sure that you're reading data that's inside of the array that you've declared. Now, you can do this for a surprising amount of time, actually. Let's just see what we get here. So instead of reading one extra element, I'm going to read 500 elements. Let's see if this works, okay? It did, surprisingly. So, I need to increase this. I want to show a thing. All right. Give me more. 10,000 should do it. There we go. That's what I wanted. So, it will just keep reading and keep reading and keep reading and keep reading and keep reading until you hit a thing called a segmentation fault. What a segmentation fault is is it's the operating system telling your program that it is trying to read data that doesn't belong to it. Another way of thinking of it is that you have exceeded, you're trying to read outside of the current stack frame. So, although C is not monitoring whether or not you're reading inside of the data type, inside of the array that you've declared, the operating system is monitoring your program to make sure that it's not reading or writing to data that hasn't been allocated to the program. If it violates memory access in this way, it produces a segmentation fault. Segmentation faults are extraordinarily common when working with arrays. You're likely to see them. What it means is that you failed to correctly specify the end condition for your data structure. Now, anytime you are using an array and exceeding the bounds of that array by accident, because nobody would ever intend to, right? There's always a possibility of a segmentation fault. However, a segmentation fault may only show up once out of every 10,000 times you run the program, because it depends on the placement of the array that you're reading from in memory, right? So if you imagine this is your stack frame, right? And your array is allocated here, right? You've only got this little bit to go, right? So if you're only reading like 3 values over the end of the array, you know, it requires your array to be that close to the end in order to cause a seg fault. However, if your array is like towards the top, you know, and you're overstepping it by 3, you know, however many, you might not see that error, like for, you know, you might not see that error for 9,999 out of 10,000 executions. Particularly if it's an off by 1 error where you're just reading 1 over the bounds that you want it to, right? Make sense? So, I'm about to bake your noodles even further. It doesn't just do this for reading. You may also assign to memory outside your array. In this example, all we're doing is reading, right? But equally, you could have foo I is equal to some other thing, and the C program will dutifully perform that assignment operation for as long as you're requesting it, until the operating system tells it to back the F off. Question?
Is there any system to where the array is placed in memory?
No, it's essentially random. Although it's like, it's arbitrary but deterministic. So like, you're not privy to the decisions that the operating system is making about where your memory gets put, but like, computers are incapable of true randomness. So like, there is some system to it. It's just like too complicated for mere mortals to be able to, you know, figure it out. Linus might know. Any other questions? Yes?
Sorry. What does the second printf output?
Which one?
Second.
This one?
Yes.
Oh, it prints foo out as a pointer. That's P for pointer.
Oh.
Yeah.
So ls is.
That's ls is long string. So I think something like that. I forget. I don't know. This is from a previous class. It's something I forget what I was doing here. But are there any other questions about arrays? This truly is programming in the Wild West. You're the sheriff. I think I lost battery. test. There we go. Like, yeah. So you can imagine that, you know, a lot of the early viruses and stuff took advantage of this sort of thing. Yes?
Am I just going crazy, or those first couple times you ran this, were there 13 items in the array? I was wondering, like, is that a consequence of like this array indexing? Are you defining the length of the array up there, or are you defining the last item indexed?
Excellent question. When the number that you put here is the number of elements in the array. So if you declare it with 12, there are 0 through 11 declared as indexes. Does that make sense?
Yeah, I'm just wondering, I swear I counted and there were 13.
Yeah, that's because I was doing an example where I like asked for one more than the end.
No, I mean like the first time.
Oh, really?
Yeah, I might just be crazy, but.
Well, I can put it back the way it was, and we can take a look. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Cool. Question?
Back to the previous question. So the first string is the location of which is printed by the first printf, right? Oh no, second printf.
Yeah, this one I guess isn't doing anything here for some reason. I should probably just remove it. But yeah, this P prints out the memory location of a pointer. Arrays are pointers, so you can view the actual physical location they're stored in memory, expressed in register. Basically, register memory is the most efficient form of memory in terms of speed, but and C will allow you to suggest to the compiler that a particular variable gets stored in register. This is the sort of thing that, like, if you turn optimizations on, GCC will figure out which of your variables are more efficiently stored in register memory as opposed to regular memory anyway. So it's like, this is at best a suggestion, right? You can say, hey, GCC, I suggest that you store this variable in register memory. And GCC will be like, well, I will consider your suggestion. But that's about as far as it goes. Whereas these are like, you know, much more, you know, you actually take control. C cannot give you access, full undiluted access to register memory. Most architectures I've seen only support 16 registers. So you can imagine that you would run through them pretty quickly if you were like, oh, register memory is more efficient, so I'm going to make all of my variables register memory. Yeah. I'm going to make 300 register variables. It's like, yeah, okay. So, let's talk about arrays then. Yeah, I'm running out of time, so I'm going to skip this. Skipping, all right, so. In Python, you have many data structures to choose from. Tuples, lists, dictionaries, sets, and strings. In C, there is only one, the array. If you need something more complicated than an array, you have to either find a library defining it, or define it yourself. C, so it's not like these things can't exist in C, because that's how Python implements them. Because Python, a lot of it under the hood, is actually in C. So, like, you can have dictionaries, but you have to find a library for them or write them yourself. And, you know, generally you're sacrificing a lot of efficiency for them anyway. So, what is an array? An array is a continuous and contiguous set of segment of memory which may be accessed via linear indexing. So basically, it's like somewhere between a list and a tuple. So statically sized right? So basically, when you declare an array, they get declared with a certain size, right? The system allocates you a set of a block of memory, that precise size, and that does not change through execution. That is a property of arrays. Yes.
I remember that there are some algorithms need to, like double the size of array during the, when the algorithm was running. So this kind of algorithm cannot be implied in C.
It cannot be implemented in C without using dynamic allocation libraries.
Oh.
So you can create arrays which can be resized, but right now we're talking about the sort of native static arrays. We'll talk about, like, in order to understand dynamic arrays, we really need to do pointers, and we're going to do that next week, right? Basically, you can't create an array using the static array syntax and then resize it. You must create the array using the dynamic allocation libraries. Then it can be dynamically changed. That's because it gets stored in different memory, right? Pretty sure this gets stored in the call stack. Properties of arrays, which are different from properties of tuples and lists and all the rest of the Python data structures you know and love. All elements of an array have the same data type, right? Not only are they statically allocated, they are monotyped. So this business in Python where you can have a string here and an integer there, no. Everything is integers, or everything is characters, or everything is pointers, one data type. Arrays use zero indexing for reasons that we're going to explore when we get into pointers. But that should be no surprise. Arrays are static. The size of an array does not change during execution. This means that the size of the array must be known at the time of declaration. There are ways of getting around this, but not without using pointers, which we'll talk about soon. So basically, So, an array is declared in the following manner. Int C square braces size indicated. X here is the size of the array. Note that X must be either an integer literal or an expression which evaluates to an integer, like 5 plus 7. This rule applies to array indexing as well as declaration. On declaration, arrays are filled with smelly garbage, junk data, meaningless sequences of zeros and ones. Arrays may be indexed using the array index operator, which is the same in C as it is in Python. Open square brace, number, close square brace, that accesses a particular element of an array. So unlike tuples in Python, the elements of an array may be assigned to. So this is a valid statement, right? Any questions so far? Yeah, this should be reasonably straightforward, right? This operation binds at the same level as function calls, so very tightly. So it binds so tightly that most people don't even think of it as being an operator, but it is actually an operator. If you dig into it, we'll see that next week. As we'll see later, the index operator is actually syntactic sugar for some pointer operations. But again, we need to talk about pointers first, so we'll leave that for next week. So, here's an algorithm for pretty printing arrays. Pretty printing just means printing in a way that's pretty. Sometimes the terminology is exactly what it sounds like. So, include stdio.h, sure. We have main, we declare an integer array of 12 elements. We declare a floating point array of 4 elements. You know what? Let's just run this thing. This is not quite what I was expecting. Okay, so here's the program. We'll compile arrays.c. So, this is how you declare a string, right? Foo is actually too large for the declared size. This is an array that's been declared with 2 elements, and this string actually contains 4 elements, despite the fact that it appears to contain 3. The reason for this, as we're going to see later on in this lecture, all string literals are implicitly terminated by the null character. That's how, that's like a very, very old convention that's built into the standard libraries, which lets the string libraries know when it's reached the end of a string so that it can stop processing. Basically, when you're programming with arrays, there are a lot of things which don't exist. There's no length function. So if you pass, there's a size of function, but it only applies when the thing's in scope. If you pass an array into a function, you must also pass the size of that array into the function if it does not contain a terminating character or a terminating value, like a known terminating value. C does not know how large its arrays are. You have to tell it how large its arrays are. So, for example, when I'm printing all of the elements of this array, right, I'm actually hard-coding the size. Let's run this thing and see what it does. Yeah. So in the first place, foo itself is a memory address. This is what a memory address looks like. Second of all, notice how I'm declaring it as size 12, right? But I'm not initializing it anywhere. It therefore contains random values. These are the random values. Those are the random pieces of memory that are applied. And you can see that every time I run this program, I'm getting different values. It's garbage data. Although there are patterns to it, those patterns can't be relied upon and do not indicate anything meaningful, right? So here's a little fun thing. This thing is supposed to be of size 12, right? What happens if I put 13 here? What would happen in Python?
Get an indexing error?
You'd get an index error because index 12 is not included. right? Because 11 is the last one. So what happens if we do this? It just doesn't. It has read and printed an element that is outside of the scope of the declared array. It is also containing garbage data, but it's done it. Not only that, did we get so much as a warning? No. That's that warning from here earlier. Welcome to the Wild West. This is C programming. I'll just let that one sink in for a moment. So there's a reason that this happens. Basically, your array is a pointer to memory. The indexing operation is pointer arithmetic. It just moves the pointer over, however many spaces and then reads that value, right? And then does whatever you want with it. But the fact that we were able to do this means that C isn't checking to make sure that you're reading data that's inside of the array that you've declared. Now, you can do this for a surprising amount of time, actually. Let's just see what we get here. So instead of reading one extra element, I'm going to read 500 elements. Let's see if this works, okay? It did, surprisingly. So, I need to increase this. I want to show a thing. Okay. Give me more. 10,000 should do it. There we go. That's what I wanted. So, it will just keep reading and keep reading and keep reading and keep reading and keep reading until you hit a thing called a segmentation fault. What a segmentation fault is it's the operating system telling your program that it is trying to read data that doesn't belong to it. Another way of thinking of it is that you have exceeded, you're trying to read outside of the current stack frame. So, although C is not monitoring whether or not you're reading inside of the data type, inside of the array that you've declared, the operating system is monitoring your program to make sure that it's not reading or writing to data that hasn't been allocated to the program. If it violates memory access in this way, it produces a segmentation fault. Segmentation faults are extraordinarily common when working with arrays. You're likely to see them. What it means is that you failed to correctly specify the end condition for your data structure. Now, anytime you are using an array and exceeding the bounds of that array by accident, because nobody would ever intend to, right? There's always a possibility of a segmentation fault. However, a segmentation fault may only show up once out of every 10,000 times you run the program, because it depends on the placement of the array that you're reading from in memory, right? So if you imagine this is your stack frame, right? And your array is allocated here, right? You've only got this little bit to go, right? So if you're only reading like 3 values over the end of the array, it requires your array to be that close to the end in order to cause a seg fault. However, if your array is like towards the top, you know, and you're overstepping it by 3, you know, however many, you might not see that error, like for, you know, you might not see that error for 9,999 out of 10,000 executions, particularly if it's an off by 1 error where you're just reading 1 over the bounds that you want it to, right? Make sense? So I'm about to bake your noodles even further. It doesn't just do this for reading. You may also assign to memory outside your array. In this example, all we're doing is reading, right? But equally, you could have foo I is equal to some other thing, and the C program will dutifully perform that assignment operation for as long as you're requesting it, until the operating system tells it to back the F off. Question?
Is there any system to where the array is placed in memory?
No, it's essentially random. Although it's like, it's arbitrary but deterministic. So like, you're not privy to the decisions that the operating system is making about where your memory gets put, but like, computers are incapable of true randomness. So like, there is some system to it. It's just like too complicated for mere mortals to be able to, you know, figure it out. Linus might know. Any other questions? Yes?
Sorry. What does the second printf output?
Which one?
Second.
This one?
Yes.
Oh, it prints foo out as a pointer. That's P for pointer.
Oh.
Yeah.
So ls is.
That's ls is long string. So I think something like that. I forget. I don't know. This is from a previous class. It's something I forget what I was doing here. But are there any other questions about arrays? This truly is programming in the Wild West. You're the sheriff. I think I lost battery. Test. There we go. Like, yeah. So you can imagine that you know, a lot of the early viruses and stuff took advantage of this sort of thing. Yes.
Am I just going crazy, or those first couple times you ran this, were there 13 items in the array? I was wondering, like, is that a consequence of like this array indexing? Are you defining the length of the array up there, or are you defining the last item indexed?
Excellent question. When the number that you put here is the number of elements in the array. So if you declare it with 12, there are 0 through 11 declared as indexes. Does that make sense?
Yeah, I'm just wondering, I swear I counted and there were 13.
Yeah, that's because I was doing an example where I like asked for one more than the end.
No, I mean like the first time.
Oh, really?
Yeah, I might just be crazy, but.
Well, I can put it back the way it was, and we can take a look. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Cool. Question?
Back to the previous question. So the first string is the location of which is printed by the first printf, right? Oh no, second printf.
Yeah, this one I guess isn't doing anything here for some reason. I should probably just remove it. But yeah, this P prints out the memory location of a pointer. Arrays are pointers, so you can view the actual physical location they're stored in memory, expressed as a decimal number. But again, kind of conscious of the time. That's for next week.
So can we add a point symbol? I remember it's what?
Which?
What it is? The symbol of the pointer. I mean, if we add it before a variable, then it means the pointer of the
Star.
Yeah, if we add it before the for and replace the p to other, can it still show the address?
Yeah. You could actually put a star here, remove this entirely, like malloc, like dynamically allocate 12 memory cells and then all kinds of stuff. But again, I kind of have a lot of slides to get through. Yes?
For the last 2 lines.
Yeah.
What are they doing?
So this one is printing out the last, the third element of a data structure that contains 2 elements. It's here. Here I go. There. I was showing things with characters. Basically, I've got this string, right? I view element 0. It's the it's not showing up. It's F, and the ordinal number is 102. So if you look it up in an ASCII table, it'll be 102, right? But basically, the point of that demonstration is characters are only characters if you interpret them as characters. They can be integers as well if you interpret them as integers. Make sense? Okay. Because everything is just numbers. Even letters, just numbers. Okay. Good Lord. All right. Skip that, skip that. Skip that. So. Just like a lot of things in C, there are no free lunches. You can't print a whole array just by passing the array's name to printf, as the identifier, the array identifier is really a memory address or pointer. So you can't just print arrays like you can in Python. You have to actually print the elements. So an uninitialized array is full of garbage data. To initialize array, provide a comma-separated series of type-correct literals or expressions delimited with curly braces. So, this is the correct way to create an array that has elements. If the initializer is smaller than the declared memory in C will backfill with zeros. So if you declare space for 12 and you only provide 4, it will put zeros in the rest of them. If you initialize the array, you may omit specifying the size. The size of the initializing array will be used. So if you'll notice in this example, I have not provided a number here, but it's 4 because I have 4 elements there. Right? Make sense? Cool. Sorry, I'm going to have to run through this reasonably quickly. So, consider the following function prototype. Int star my function const int input. Input is declared as an array by the inclusion of the square braces. You could also use int star, which is pointer. This int star tells us that the function returns an integer pointer. Arrays in C are basically syntactic sugar for pointers with a couple of read-write protections. The constant term locks the pointer so that it can't be modified, essentially making the pointer read-only. So it's like the name itself, input, can't be modified, but the individual elements can be because they're different memory cells that are indicated by the memory reference. If you want to be able to modify the array, just leave out the const keyword. You can do this with any argument, not just arrays. So, size up. In Python, we have the length function to quickly and easily tell us how large our data structures are. The equivalent in C is size of, but as with most things in C, it's a bit more complicated. Size of returns the size of the thing that you give it in bytes, provided that in bytes that the provided argument was declared with. So size of is a function which finds the actual footprint in memory in bytes, right? So if you want to find, for example, the number of elements in an array, you must take the raw size in bytes and divide by the number of bytes in each element. So it's like size of foo divided by the size of the first element of foo. Or if you know the data type, just say, size of int. That also works. You want to use this type of thing instead of hard coding these values because that makes your program portable to architectures that may have different definitions for the size of integers, which exist in embedded systems applications most particularly. So, size of may be used on variables of any type, not just arrays. Accordingly, the declared length of an array is equal to the size of the array in bytes divided by the size of any element of the array in bytes. Does that make sense? A little bit? If you pass an array into a function, size of no longer returns anything of value. So you have to pass the length in to the function as an argument, typically. There might be ways around it, but that's the way I've been doing it. So, accessing higher dimensions. Linear arrays are all well and good, but what if I need to represent a matrix or a checkers board or something with 2 dimensions? What if I have to represent something with 3 dimensions? The way that you declare a 2D array in C is you simply include 2 of the square braces. You may also declare them with size, right? However many square braces you include, that is the dimensionality of the data structure. You declare literals by just having nested series of curly braces. Sorry I'm going through this reasonably quickly, but class is drawing to a close and I still have a section I didn't get to. Dimensionality is indicated by the number of square braces following the identifier. These are correctly thought of as arrays of arrays. Providing n minus k indexes to an n-dimensional array will produce a k-dimensional array. So, very quickly, the way that these things are stored in memory is like that, right? Right? Make sense? If you have a 3-dimensional array, then just imagine this like popping out of the board, yeah. So, strings are character arrays. This is the same as that. Notice the null character at the end. This thing is dead, isn't it? I'm just going to take it off. Yeah. So, in Python, strings are kind of their own data type. They're like their own type of data structure, right? In C, a string is just an array that happens to contain characters. The only difference is that the last element is always a null terminating, the last element is always the null character. We say that strings are null terminated. This is so that when you're looping over the characters in a string, you know when to stop. This only works for strings because they're like, if you were to do a similar thing in integer arithmetic and like use 0 as a terminating number, 0 is actually used quite frequently in integer arithmetic. Like there's no good integer to say this is not an integer and it's a code, right? But in characters, every character is a code, so it's easy to just pick one and say you are a code that says this string is now finished. Does that make sense? So, you can use the double quote notation as a syntactic shorthand for having to do a, curly brace, single quotes, comma, delimited thing of all the individual characters, which of course would be a huge pain in the butt, as you saw from the previous slide. So, fine. If we specify a size larger than the string itself, we get the following. The three characters, BAR, and then null, 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 which is actually the same way that it works with integers as well. It backfills with zeros. The code for the null character is just 0. If you were to interpret the null character as an integer, it would be 0. So at least it's consistent. Any questions about any of that so far? So, string isn't even a proper word. It's not a keyword in C. If you try to declare something as type string, it won't work, unless you've included a library that allows it to work. Character arrays may be indexed just like regular arrays. Basically, all operations which apply to regular arrays apply to string arrays, or character arrays, because they are arrays, including the thing where you can read past the end of them. String literals are always terminated by the null character implicitly. All strings must be null terminated. We can receive strings directly from scanf using the %s format specifier. And if you put a number here, that specifies that you're limiting the amount that you're reading to 14 characters. You have to remember to leave space for the null character. By inserting a number, the format specifier may even be used to limit the number of characters that get copied into the character array. Foo is actually a pointer. We don't need the address of operator. Remember, like scanfs that we did with integers, we had to include the ampersand, right? That was extracting the memory address from the integer variable, passing that to scanf. Because this is already a memory address, we don't need to include the address of operator. In fact, to include it would be a crime. So, foo is already a memory address. All right? Any questions? I know I'm going through this quickly, and I apologize.
Why 4 is actually a pointer?
Sorry?
Why the 4 is actually a pointer?
What is a pointer?
No, why the 4 here is a pointer? We didn't add any star symbol.
Because it's like from the previous. Yeah, I suppose the declaration isn't here, but it's a character array. Arrays and pointers are the same thing. They just have a few more read protections. So, a common form of security vulnerability in C and C++ programs is an array overflow. So, it turns out that because you can write past the end of a data structure, if you don't require scanf to only read a specific number of characters, the user can actually write as much into that as they want, completely overflow the data structure, overwrite other variables, insert arbitrary code if they know how, all kinds of nasty things. So, arrays are replaced with pointer arithmetic by the compiler with no bounds checking. If you tell C to write 100 characters into a 50-character array, it will happily do so. The extra 50 characters will be written into memory that comes after the character array. This can overwrite all kinds of useful things like other variables or other data structures. If the character array is stored in the stack, function call information may also be vulnerable. The moral of the story is that you should always limit the things you write into an array to the size of the array manually. So, let's see, this might be, I don't have a last slide, Conic? Oh man. All right, so I should have this one. If you guys will just bear with me for like 2 minutes, I'll show you what a stack smash looks like. So, let's see here. Yeah. Gcc bounds.c out bounds. Sure. That's not so nice. Let's just put S there because that's how it's supposed to be. So, define. It's using a define statement. That's fine. We'll just replace it for this. Right. So, very quickly. When you're taking input from the user, you have to, because these are static arrays, you have to declare how much space you're willing to give the response manually. In this case, we're giving it 10 characters, right? Like, for a yes-no response, that would be more than enough, right? We prompt for a query, we read that query, and then we echo it back. But notice there's no protection that's been placed on the number of characters being read. So, if we execute this, enter a query. Okay. The query is okay, right? Enter a query that's longer than 10 characters. My father ate my fries. Why is it not? Oh, yeah, it's probably just separating it. If I did it, my father ate my fries. There we go. We run out of stack. Actually, this one happened pretty quickly. Maybe they've updated to clamp down on this more quickly. So that's how many characters is that?
I think it's 10.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ah, all right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep. So if we exceed the size that we're writing to, the operating system will clamp down on it with an error pretty much immediately. So yeah, that's a stack smashing attack. Or at least that's how stack smashing is now dealt with. Any questions? Yes?
I know we've covered this. Scanf is the part where it's reading the
Yes.
thing that comes in. Perfect, thanks.
Yeah. Roughly equivalent to Python's input function.
Right.
The format specifier basically tells you whether you're reading a string or an integer or a
Right.
character or whatever. Any other questions? Okay. All right, good luck on lab today. It's easier than lab 3. Take her easy. I'll see you when I get back.